All right, here we go. We got 4.1 rational exponents. Our learning goal is to simplify expressions with rational exponents. You guessed it. Now, before we do rational exponents, we're going to do a little math talk about negative exponents here. And I want to prove to you really quickly why these work. They will be included in our rational exponents, so we need to know that, right? Now, normally when you see a negative exponent, you might remember that you have to put it underneath 1 and then raise it to the positive power now, okay? And we're going to prove that in a second. And then that would mean that this is 1 over 8, okay? Now, a lot of people, they're exposed to the rule, to the property, and they go, okay, boom, put it under 1, make it a positive, then evaluate. Okay, but why is it like this way, right? When we do a property, we're saying it's a shortcut. We're saying we can make these steps and they work. Well, why do they work, right? So let's do this. Let's do 2 to the power 1, 2 to the power 2, 2 to the power 3, okay? 2 to the power 1, we know is 2. 2 to the power 2 is 4. 2 to the power, I just wrote 2, is 4. And 2 to the power 3 is 8, okay? Now, if we look at the pattern happening and we look at it going this way, right? We are multiplying by 2. Each time we increase the exponent one place, right? We're multiplying by another 2. Well, what happens if we're going this way? That must mean that we are dividing by 2. And with these, positive exponents here, it makes lots of sense. 2 times 2 is 4. 4 times 2 is 8. We get to the end there. 8 divided by 2 is 4. 4 divided by 2 is 2, okay? And so we can keep this pattern going. So that must mean that 2 to the power of 0, and that's kind of proving this here, is 1, right? Because we went from the previous one. 2 divided by 2 gives us 1. So if we keep this pattern of dividing by 2 going to the left, and we keep subtracting 1 from the exponent's place, well, 2 to the power of negative 1 must give us 1/2. Because to go from this positive 1 here and keep that pattern dividing by 2, well, 1 divided by 2 gives you 1/2. Which means then 2 to the power of negative 2 is 1/4. And then 2 to the power of negative 3 gives us 1/8. We're able to achieve this by dividing by 2 when we look at this pattern to the left, okay? Now, that's when we realize, well, wait a minute. Isn't that just the same thing as taking this, throwing it under 1, and evaluating it in the bottom's place? Because look at the pattern. 2, 4, 8 to the right, and look at the bottom. 2, 4, 8 to the left, but it's in the bottom's place. So when we see the pattern and we know it'll work that way, we just go, oh, okay, put it underneath 1, make it a positive, evaluate it there, and we can just jump to the answer, okay? But I want you to see this pattern because it helps us understand why 2 to the power of 0 is equal to 1, and it helps us see why negative exponents end up down here, okay? Now, this is what the official property looks like. Basically, when you take a variable to the power of a negative exponent, you need to put it in the bottom, put it in the denominator's place, and then evaluate it. Okay, let's look at the next one, all right? So that brings us to rational exponents, okay? Now, rational exponents, I don't want to say that they mess with our mind, but they kind of do. They don't seem to be as clear as those negative exponents, right? We're going to take 16 to the power of 1 over 4, right? Okay. Well, when we get something like this, what we generally do is we call the top one the exponent. We call the bottom one the root, okay? And so we take this and we rewrite it as the 4th root of 16, all of that to the power of 1, okay? Now, if you're confused, remember, the 1 was the exponent, the 4 was the root, okay? Now, let's think about this. The 4th root of 16. When we are looking for the 4th root, right, this just means we're looking for the same number that multiplies 4 times, right? When you took the square root, we were just looking for pairs, but now we're looking for quads, right? So we need a number that multiplies 4 times to get 16, and the answer to that would be 2. we know that 2 times 2 times 2 times 2 gives us 16, right? 2 times 2 is 4, 8, 16. So the fourth root of 16 is 2. Now we still have that power of 1, and so that would become just 2. Okay. Now, a lot going on there, right? This one is a little bit more tricky to prove, okay? And to prove it in a way that makes a lot of sense, all right? Now, let's do another one before we kind of start talking about that, all right? We have E over R. Now, keep in mind, E over R, this is what I do, all right? There's a official property I'm going to show you in the next page. They use different variables. I use E over R because I want you to see exponent over root, right? I could use P over R, power over root, but I just want kids to remember E over R because that's the most common mistake I see with these is people, thinking the bottom is the power and the top is the root. So E over R, okay? So this becomes the third root of 8 and all of this to the power of 2, okay? All right, let's evaluate that. Now we have the third root, so we are looking for a number that multiplies 3 times. In these early examples, we're using 2 a lot. You can see 2 times 2 is 4, 4 times 2 is 8, right? So that would be 2. And now it's 2 to the power of 2, which brings us to 4. Okay. Now, there's a lot going on here, I know. If you're struggling to see, where, third root of 8, let's say it was a third root of 64 or something like that, and you're struggling to go, I don't just see the answer, right? That's where your factor tree comes in. You could break it down, right? You have 4 times 2, 2 times 2, and look at this. These are our prime factorization. You have 3 2's. So that's how you know, okay, I could pull that out as a single group, okay? All right. Now, let's look at the official property, okay? Let's go back here, or over here. Now, the official property says that when you have a number x to the power of m over n, it could be equal to this, the nth root into the m power, right? Okay, but notice there's this and there's this that say relatively the same thing. When we look here, we see nth root, m power, but look at the location of m. It is inside of your radical. And then over here, look at the location of m. It is outside of the radical. So which one do you do first? And this is saying, look at these 2 equal signs here. We're saying that these are the same thing, okay? So what does that really mean, right? Let's go back over here, okay? Now let's write this step again, but let's apply the power first. So we're saying the third root of 8 to the power of 2. Well, 8 to the power of 2 is 64. So now we would have the third root of 64. And the third root of 64, well, I know what the answer is off the top of my head. I'm going to break that down with you guys, though. That's 16 times 4 gives you 64, right? 16 breaks down to 4 times 4. Now, I know these are not prime numbers, but I do have a group of 3, right? So the third root of 64 is 4. Notice that we got the same exact answer. What we're trying to tell you is that you can do root and then power, or you could do power and then root. The order doesn't matter, but which one is better? And I'm going to say this one. You should prioritize making your numbers smaller first before trying to make them bigger. Think about this. When we did the third root of 8, we made the number smaller, and then we took the power to be 4. Well, when we did 8 to the power of 2, well, powers make our numbers bigger. So then we had to do the third root of 64. Now, that's still not too big of a number. It's a number we see kind of regularly. But what if this was like, 25 to the power of 7? That would be making this number very, very big. So I would prioritize making my numbers smaller before making them bigger. Okay? All right, rational exponents. Let's focus on one thing first. So I'm going to do the top 2, and I'm going to have you do the bottom 2. In this step here, we're only focusing on the rewriting part. I know that here I went to, all the way to simplifying, and that is what our goal is going to be. But on this step, I want to focus. Let's just rewrite these, okay? Now, 7th root of 128. I know we don't see a power here, but if you don't, we assume it is 1. So to rewrite this, you take your radicand, which is a number underneath the radical, and you write it here. And then it's to the power of 1 over 7. Remember, E over R. Okay? And this would be rewritten as a rational exponent. This form over here to the left is called radical form. Okay? Radical form means it's written with the radical, and then this is technically called exponential form because it's written with an exponent, but both of those are the same thing. Okay? Now, the square root of 44 to the power of 3. Okay? Now remember, we write our radicand, 44. We have it to the power of an exponent. That would be 2 over 3. Now, you probably are just like, whoa, Mr. Fair, I'm going to call you out. You made a mistake, right? Negative, okay? When we don't put a number here, it's the same thing as if I put a 2, not a 1. I know we're so used to like, oh, when we don't see something, it's, means it's to the power of 1, right? But for roots, technically speaking, we should write the 2, but because the square root is the most common one, we just, we go, well, we're going to use this one all the time, so I don't want to write an extra 2, okay? So when you don't see the root number, it's a 2. So this is the same thing, okay? All right, now I want you to take a try on the next 2. Give these a go and rewrite these, but before you do, okay, just pay close attention on this one, okay? All right, give it a try. Okay, so for Edpuzzle here, I'm going to kind of do these separately, right? We would rewrite this one, 625 to the power of 2 over 4. This would technically be an acceptable answer. Okay, however, if we can simplify that 2 over 4 to be 1/2, which is the same thing as 2 over 4, we should do that, okay? So I would take either of these for now, but we should prioritize the simplified one, okay? Now this one on the right, let's look at it this way, right? We write this as 89 to the power of -4 over 6, which is probably what you did. And then maybe you simplified this and you're like, hey, that's 89 to the power of -2 over 3. That's fine, right? Okay. Now, this is where I'm going to introduce something to you. If you put this as your answer, you're fine because that's what I've showed you so far. But let's take a dip back to our negative exponents. We don't want to write negative exponents. We don't want to leave negative exponents in our answers at all. Okay? So when you see these, you need to rewrite them. Well, what do we do with negative exponents? We send them underneath 1 and write it as a positive exponent. So 89 to the power of 2/3. This is how we're going to leave them from now on. Now, Edpuzzle should have taken this or this, and it should have taken this or this, okay? But from this point on, let's simplify all the way. We should never leave a negative exponent, okay? All right, we got more to do. I'm going to do the top. You guys are going to do the bottom. Here we do want to simplify, okay? So 49 to the power of 1/2, all right? So that means that's the same thing as the second root of 49 to the power of 1. I hope you notice something here. When you take a number to the power of 1 over 2, it's just saying the square root. So that means if I said 49 to the power of 1/3, that's the same thing as taking the cube root, okay? Just cross that out. All right. Now, the square root of 49 is 7. 7 to the power of 1 is just 7, okay? Let's do the next one. 8 to the power of 2/3. Would you look at that? A duplicate. Shame on me, okay? You get the third root of 8. Remember, E over R to the power of 2. Third root of 8 is 2. 2 squared is 4. Now, 27 to the power of -1/3. Okay, let's deal with the negative first because it'd be hard to, deal with it second, okay? So we're going to send this underneath 1. So 1 over 27 to the power of 1/3, which then we deal with that radical. So remember, 1/3 is the same thing as saying the cube root. So this is 1 over, let me zoom in here for you guys, 1 over the third root of 27. Well, Well, the third root of 27 is 3, right? 3 times 3 is 9. 9 times 3 is 27. So this becomes 1 over 3 as your answer. Okay? Now, you may see that I didn't write the power 1 because I knew it wasn't going to change anything. All right? So here's your next 3. Give them a try. Okay, hopefully you did the first one, right? This becomes, fourth root of, oh no, let's deal with the negative. Shame on me. This becomes 1 over 16 to the power of positive 5 over 4, okay? Which becomes the same thing as 1 over the fourth root of 16 to the power of 5. I really need to zoom in on that. Okay, remember, E over R. The fourth root of 16 is 2, because 4 2's being multiplied together gives you 16. So that becomes 1 over 2 to the power of 5. And 2 to the power of 5 should be 32, right? Because if 2 to the power of 4 is 16, 2 to the power of 5 is 32. So our final answer should be 1 over 32, okay? Now, I highly recommend knowing your base 2 numbers. Base 2 numbers means, all the 2 to the power of whatever. It's the most important number, most important base ever, right? Your computers all operate binary. That's base 2 options, okay? And so, even think about memory. You buy an external hard drive or your computer. They might say it's 1 terabyte, but it's not actually 1 terabyte. It's 1,024 gigabytes, okay? And if you notice 1,024, it's a base 2 number, right? So look, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024, all base 2. And those are all the things that you see for memory storage. Okay, let's try the next one. Here we go. There is no negative exponent, E over R, so that becomes the second root of 100, which I technically didn't have to write the second root there, right? Because it's just implied. The second root of 100 is 10. 10 to the power of 3 is 1,000. Okay. Let's give the next one a try. 32 to the power of negative 3 over 5. Let's deal with the negative exponent. 1 over 32 to the power of 3 over 5. Okay. 1 over 32. Oh, yeah. Okay. That becomes 1 over the fifth root of 32 to the power of 3. And again, look at that, the importance of knowing your base 2 numbers, right? 2 to the power of 5 is 32. So look at it, fifth root of 32. So that must mean that this is 1 over 2 to the power of 3, which is really just 1 over 8, okay? It is very important to remember that pattern of base 2. It'll be your friend. Now, when you think of base 3 and base 4, those are important too, but they increase in value super, super fast, okay? And so you only need to know a smaller amount of them generally. Okay, let's go to our next concept. Okay, so with these, we want to be able to do some of them with the calculator sometimes. And the reason why is there are a lot of situations where in an applicable use of rational exponents where the numbers are extremely difficult and too difficult to do by hand. And so we want to bring in that calculator sometimes. And I'm going to show you exactly how to input it into the calculator. But this form, to me, is generally the easiest to input into a calculator because all I really have to do now is take 85 and take it to the power of whatever 1 over 6 is. And so I would convert all these to exponential form. And that would be 5, oh my goodness, E over R, let's go. 4 over 5. I think it might be safe to say that I've made it through this one unscathed, but we're just going to have to see. Okay. Now, I would get out your calculator for these. I know it says I do and you do, so I'll have you guys do the last one on your own, and I'm going to do the first 2 with a calculator. Okay. All right. Let me see if I can get this calculator up. Okay, so the first one was 85 to the power of 1/6. So, sorry, this is a free calculator. So you go 85, and I'm going to do the power, which is see just x to the y. It just lets me choose the base and the power. And then I like to put the parentheses so that I can see, or so I can just make sure that the 1 divided by 6 works, right? Remember, 1 divided by 6 or 1 over 6, same thing as 1 divided by 6. So that would be 0.16. And so now I have 85 to the power of 0.16, and I should get 2.096, blah, 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 blah. And these problems you would want to round to whatever the directions say. So I'm going to probably say that would be the hundreds place. So this would really, end up being 2.1. Okay. So that would be your answer for that, 2.1. Okay. Next one, 187. Press my x to the power of y. I use my parentheses. All right. And we had 3 over 4. Close my parentheses. 3 over 4 is 0.75. Same thing. We'd round to the hundreds, so it would be 50.57. Okay. Now, the next one, let's see if it gets back here, is 20,736 to the power of 4 over 5. Give that one a try, and let's see what you get. Okay, so let's do it. 20,736 to the power of 4 over 5. And that's what you get, 2,840.40, or just 0.4. Okay. Now, let's head back to our lesson here, right? This is really the end of it, except for, I want to talk a little math talk here, okay? Little y rational exponents, all right? And, you probably have heard this quote, but, it's a very famous quote from Albert Einstein. It says, compound interest is the eighth wonder of the world. He who understands it earns it. He who doesn't pays it, okay? And what we mean by that is compound interest. I mean, this is a loan. That's what that really means, right? You get a mortgage on a house, you have compound interest. You borrow $100,000, you don't pay back $100,000, you pay back interest. That interest compounds annually for generally 30 years, turning a $100,000 house into maybe $150,000, $175,000, sometimes even more, depending on your interest rate. Those who don't understand those numbers can get easily fooled by different types of loan packages, like fixed rate versus adjustable rate. Adjustable rate loans, they kind of trick people into thinking that they can afford it. And, because they start at a super low interest. And then people don't realize that after 5 years, it all of a sudden becomes more than what a fixed rate would be for a longer time. And that's what he really means. He who doesn't understand it pays the interest, right? So, how do rational exponents fit into this equation, right? So A is our final amount. P is the initial balance. So that'd be like the cost of the house. And then you would take 1 plus R over N, which is interest rate, over a number of times the interest applied per time, and then time elapsed, okay? Now, the number of time interest is applied per time, that's where you hear that annually, monthly, and generally mortgages are compounded annually. So that number would end up being a 1, simply because you would compound it once every year, okay? Or, actually, that could be a bigger number. But that's not really, the end is not our biggest concern. It is time. If you wanted to see, okay, I'm financing this for 18 months, okay, well, if we're looking at an annual price, that's not an 18 for T. That is a 1.5, because that's 1.5 years. Or that would be a 3 over 2, a rational exponent that goes in that place. Now, this is a basic example, but you will see rational exponents heavily involved in money. Okay, we're talking, the stock market, we're talking inflation values, depreciation values, loans, auto loans, mortgages, the whole 9 yards here, okay? What I'm getting at is it's important. All right. So I hope you guys enjoyed the video, and I will see you guys next time.